the way they teach you, everybody, including me, thinks that we live in space and we evolve in time. And psychologically, it's almost impossible to break this mold unless you're a quantum field theorist who has to live in space-time because of Minkowski and general relativity. We think here we are and things happen. So that's how we formulate everything since Newton. One of the simplest possible things that can evolve in time is a unit interval in which you take the unit interval and you stretch it by a factor of 2. Then you cut the thing that's longer than 1 and you slide it over and write this procedure as a mathematical map, which says wherever you are, you'll be twice as far away, but if you fall off the edge of unit interval, take modulo 1, and that's due to Bernoulli maps, and that was, one of the ways of thinking how out of determinism you get chaos. Basically, any condition, initial condition, and its nearest neighbors, epsilon neighborhood, in this process gets stretched, and some of them end up on left and right-hand side, and as you repeat this operation, you get all possible futures that can happen in a system like that, and that's the essence of deterministic chaos. So law is deterministic, but any variation in initial condition has very serious consequences called chaos. Everybody knows what mod 1 is, but let me remind you what mod 1 is. This map has a stretching parameter, S for stretching, some number that's larger than 1. In our case, it'll be integer, just to make it simple. And what is mod 1? Whenever the stretching gets you outside of the regime of unit interval where you want to live in confined space, you subtract the integer part and you give it name, you call it M. Dynamics in this system, you can think of it this way, is that you start someplace, and this is your field defined someplace between 0 and 1. You stretch the thing, and then you're given an instruction how to subtract from it integer part such that after this combined effect, you're still in unit interval. You can use this integer part to enumerate possible trajectories. So this integer part is integer of what S does to unit interval. So it turns out in this particular case takes values from 0 to S minus 1. This is a linear problem, you think, but it's not a linear problem because this instruction set is nonlinear. The stretching is linear, the instruction is nonlinear. And for every particular sequence of this letters M, you have different solution to linear problem. So linear problem usually has just one fixed point origin, but not now. That's where the nonlinearity crept into the Bernoulli map. Now, suppose you throw dice and you're not very fussy about how, the physics of a dice. You can model it by saying there's 6 possible outcomes. So you stretch by factor 6 and you have this alphabet. And then you see I can have 6 outcomes in one throw, but if I do 2 throws, there'll be 36 outcomes. And then there is a little subtlety you can ignore, but this point is identical as the origin under modulo 1. So there are actually 6 square outcomes minus 1. Ignore it, but here it is. So what is chaos in this very brief course on chaos? Chaos says that neighborhood stretch, that's called positive Lyapunov, in which in this simple model is a logarithm of stretching. So this is a rate per throw. That's what Lyapunov is. I have to divide it by n to find average rate. And but it's a boring thing, and everybody runs away and nobody comes back. But if you have cats confined into unit interval, they have to come back. And then you have to count how many ways they come back. That's done by these possible sequences that are allowed. So you can count them. That's a number of possible trajectories. And you have to take a logarithm of that number and find average number of ways of returning. That's called positive entropy, and that is chaos. So that would be a very childish course, but now we have to get a little sophisticated. But basically, if you think forward in time, Lyapunov tells you how your neighbors run away, and entropy tells you in how many ways they can come back. Together, you get ergodic cover of state space.